I'm Chris McEniry. I'm going to be going over some common performance patterns as seen through histograms. Just for a quick show of hands, how many people are familiar with histograms, specifically CF histograms, nodetool, etc.? Okay, so a good number of the room. So if you really want the quick takeaways, basically histograms are good, heat maps are better. There's some timing issues that you run into straight with histograms. Cassandra histograms are a good way to show the form of latency and data sizes. That's pretty much all you'll get out of them. There's only, when you move from looking at histograms and heat maps, you're really only going to have a couple different things that you can see from it, and you're going to have to interpret which paths to go from there. So, you know, with that in mind, knowing which histograms correspond to which instrumentation points inside of Cassandra is very important. And then, you know, distilling out what are some of the inherent problems or design patterns within your application versus what are temporal things with regards to operations and maintenance of Cassandra is going to be one of the things you want to see. And everything comes down to data model, data model, data model, understand it, otherwise you're not really going to be making the right decisions, right? Quick recap, what is a histogram? Just for the quick intro, it's a way of representing a bucket of data without having to keep every individual point of data. You know, this becomes the, well, you can throw a scatter plot up of everything, or you can kind of take a look at the bins and with regards to how many counts you have inside of each bin. Why do you do this? It's always the trade-off between speed and data collection versus granularity. So a couple of things to just keep in mind. What does this histogram look like? Basically, on the left-hand side, you have a bunch of data points. They get collected into bins. You count the number of data points inside of each bin, and then you record that as your final data. Pretty straightforward. A lot of people showed that they understood this, so. What is the downside here? Most of the time when you're looking at a histogram, you're looking at smoke and you're not looking at the fire. You're not really going to see what the problem is. You're just going to have some indicators, A, that there is a problem, and then maybe where to look. Those are really the only two things you're going to get out of it. So, inside of Cassandra, there's two main histogram types. One is latency. The other one is data information, size, formatting, et cetera, et cetera. And then inside those indicators, there's two main components that you're going to be looking at. The first one being your column families, up to key spaces somewhat, and then also your coordinator or your storage proxy. So what's happening at the initial request levels. Cassandra has a lot of metrics, right? So there's two main areas I'm going to talk about. The one I'm not going to be talking about as much is the Cassandra.metrics. Part of the reason is the full histograms aren't available in that for many of the items. What is kept instead is fixed percentiles. And again, this comes down to how much data are you keeping, are you trolling through, versus how much granularity do you need to come to the decisions you need to make. So the focus of today is really going to be about the Cassandra.db metrics area. This was the original instrumentation for the storage service inside of the code, and it does, as I said, it does contain those full histograms. For those of you following along at home, if you really want to dig into where, these are the actual metrics you can pull out which have the histograms. So, you know, slides will be available online, don't have to write them down right now, but the main thing, within column family, you have read and write latency, you have an SSTable per read, you have your column counts per row, and a row size in bytes per row, obviously. Inside of the storage proxy, again, you have the read and write latencies. You also have a range latency for when you're performing range operations in addition to individual reads and writes. Again, more stuff that you'll want to check the slides for. I'm not going to repeat really here. This is the actual JMX metrics, JMX bean names that you're going to want to look at for these metrics. And in here, there's a couple things. It's not well highlighted. There's something called the lifetime or total versus the recent. One of the decisions that was made was, especially with the tools that are involved, it isn't clear when you should be sampling your information, and it isn't clear who's going to be polling it or looking at it. So there is a recent metric, which is what a lot of the tools use, and it gets reset every time it gets read. So if you're operating alone, this is not a big deal. But if you have multiple people working together, or if you have a background job that's collecting metrics as well as you're doing manual metrics collection, you're going to see a lot of stuff that gets reset, and it's going to have, it may influence the shape of your data. So if you're running anything that's long-standing and it's taking a look at stuff, you want to go straight to the JMX matrix or JMX metrics and look at the lifetime or total ones. The recent ones are really going to be influenced by nodetool. Speaking of nodetool, so it has two useful commands inside of there. CF histograms, which will take a key space and a column family as its operator or as its arguments, and then proxy histograms, which we'll talk about the storage service. So when we take a look at one of these, what does it look like? Well, this is taking a look at the column family histograms, and this is looking at one particular column family. As I said, there's 5 different metrics that it's going to be recording. Your read-write latency, which are the second and third column. It has the SS tables per read, which is an indicator of how many SS tables every time it made a read. Did it need to go and touch to be able to get the data that you're collecting? Row size, column counts, just a general idea of what it is. On the left-hand side, you have an offset, which is effectively your bin numbers. General rule is that you start with 1, and then every bin number after that is 20% greater, rounded up. So you go 1, 2, 4. It's not until you hit like 10 when you start incrementing by 2 of them, because that's where your numbers go. So yeah. And then just to reiterate the fact, if you're using nodetool references the recent histograms, not the total histograms or lifetime histograms. So anytime you read it, it's going to go away. Now, the nice thing is row size and column count stay because they're not actually ephemeral running counts. They're changed only when there's actual data operations that change the SSTable sizes. So anything happening in memory won't actually be reflected there. This is something to keep in mind for later. That's what the column families look like. Proxy, or the storage proxy doesn't look very different. You know, again, you got read-write latencies and then range latencies. And I'll admit, I'm not a range person, so you'll notice that a lot of my data here shows up with a bunch of goose eggs for the ranges. So this is kind of first pass. This is what a lot of people have seen. What have we looked at? Again, when you're reading the histograms, you're going top to bottom. You're seeing that each bin is getting a little bit larger, so that the volume of data or the volume of differences at each point is much larger. In general, read latencies are take longer, are higher than write latencies. This is expected with inside Cassandra. It writes very well. Read is different. And then the storage proxy latencies are higher than the column family latencies. Again, kind of expected from the standpoint of the storage proxy operates with data responses from the column family layer. So this is kind of, you can see these actual facts inside the histograms. Pretty straightforward, right? So what can we drill down a little bit more? And this is where it starts to get, this is where you start to see some of the aliasing problems inside of the histograms. So there's this traditional problem called the bimodal hump, or the bimodal distribution or double hump. What this means is you have in a set of data, bimodal means that you have 2 modes in it, 2 areas where there are a large cluster of high frequency pieces. So in this particular data set, floating around 42, 50, 60, you're seeing 1 hump of data, and then floating around in the 2,000, 3,000, you're seeing another hump of data, okay? So the question is this expected? Is this where, does this indicate that there's a problem or what's going on? This in particular is a read latency. So we have to ask ourselves, what where can our reads come from? When we're actually doing draws, what are our reads coming from? And if we're looking at column families, this is just the first pass, right? When you do a read, Cassandra has to go in and at least touch one SS table. That SS table may exist in memory. It may exist in a row cache, depending on your setup. It may exist in the virtual file system cache of the system, which is also memory, or it may exist on disk, okay? So when it comes down to it, we have two memory-based things and one disk-based thing. So from that standpoint, it would kind of make sense to always see a bimodal distribution. You know, memory, you're going to access at somewhere between, well, memory is rated at like 60 or 70 nanoseconds. Pulling, you know, a meg of memory from, or meg of data from memory is somewhere along the lines of, you know, 60 microseconds, right? Whereas pulling any kind of data from disk, you're talking into the millisecond rate, you know, range. If you're talking rotational media, you're in the 100 microseconds on average with regards to solid state, right? So you can kind of see there might be, you know, two distributions here. Well, in reality, you're not usually going to see a bimodal distribution due to your actual hardware configurations. Because when it comes down to it, it's rare that you actually read from one SS table. It's rare that you're going to be seeing a large set of data that's always sitting in memory and some of it on disk, and depending on what you're doing, you're going to be interleaving a lot of these calls. And there's performance, you know, performance benefit or performance optimizations that the system typically has on that will try to pull in extra parts from disk and put it in memory. Now, if you were here listening to a couple talks before, that may not necessarily be the best case for Cassandra, but when it comes down to it, a lot of people have the defaults configured such that there's disk read ahead happening, there's I/O shuffling happening with regards to the schedulers. So the bottom line is that all of these contribute to making the actual read time frames not be a clear, oh, this read is from disk or this read is from memory. So you're not really going to see a bimodal distribution there. So if they're getting muddled together, what are kind of the other places we can come from? Well, one of the problems you see with histograms is the sum of two histograms is just another histogram. And once you get that sum, you have no idea what the actual individual contributors were. So if you run nodetool and then 2 hours later run nodetool again, and there were some events, some that were very fast and some that were very slow, you're not going to be able to tell that different from a distribution where it had an even setup of some events that were fast and some events were slow. So basically you see aliasing happening anytime you're running histograms. So how would we work around this? Well, you can run nodetool very often, every 15 seconds, okay? Some of the stuff that could slow down a system usually happens on a longer time span than 15 seconds. You know, common problems, read repairs, compactions, garbage collections, if you ever hit a major one. These are definitely on the, on the reads and the compactions, you can easily get into minutes to much longer on a large data set. Garbage collection, hopefully you're never hitting anything that bad, right? But the point being, there will be some time frames where there's definitely a sustained amount or sustained impact to the overall system. So we can start looking at these frequent samplings of histogram and put them together. Well, there's already methods to account for this. This is where heat maps come in. People seem pretty familiar with histograms. What do people think of heat maps related to histograms? Familiar, unfamiliar? Familiar? All right, not as many. So graphical representation, all a heat map is a time series of a bunch of histograms, right? There's other ways to form it, but in this context, that's what we're doing. So on the left-hand side, we basically have taken one sampling of histograms, turned it on its side so that we're looking at it in just another perspective, and then we're laying right next to it another sampling, another sampling, another sampling, another sampling, okay? So if we start pulling this together and we say, all right, let's go back to our original theory here and say there's a bunch of memory hits and there's a bunch of disk hits. This is what the ultimate histogram that we got, which is on the very far left of the slide, that's what it could be expanded out to when we have sampled histograms, okay? One way to interpret it, well, what if we had a period of low latency and a period of high latency? Unfortunately, that looks exactly the same when you compile it into the final histogram. But you can see over the period of time that it's very different between those two problems. So fundamentally, going back to the original problem of like, all right, we have these read double humps that happen. Are they a problem? Yes, they're a problem. And it really comes back to those memory and disk bands get commingled. You don't have a clear indicator when you're doing any given read from Cassandra that it's going strictly from memory, it's strictly from disk. So you'll be seeing a lot of things happening. So that's definitely going to lengthen out the time of any given call. So this is kind of what that looks like in reality. You're going to be, as I said, you're intermingling a bunch of disk and memory reads. So you're going to see one band that kind of sits there. You might see some harder edges on each side, but fundamentally, when you're really starting at it, you're going to see those two things. Or you're going to see that one thing rather than two distinct bands. Okay. I feel like I'm going too fast. All right. So we've taken the histogram, we've broken it down, we have a bunch of different heat maps that are generated out of the series of histograms. How do these become useful for detecting problems? Well, what you're looking for is differences. Any kind of thing that can kind of come up that will cause some shift in your data or some difference between what your expectation is and what it's actually showing. So you're going to compare times, which is what the sampling rate is really good for. You're going to compare different magnitudes. You're going to compare between column families, different usage patterns, et cetera, and you're going to look between nodes, because then you have to take a look at, are we looking at hardware problems, are we looking at difference in configurations, et cetera, et cetera. So we're going to go through just a bunch of these and what they might look like on an actual heat map. So load spike. Pretty straightforward. We expect to see that there's going to be an increase in the number of requests coming in, so we're going to get a much darker heat map in general. And at the same time, we're probably going to see a shift towards higher latencies. Okay? If we're seeing a bunch of reads come in, we're going to have contention, something's going to happen, we're going to have to worry about that. So that's what this heat map looks like. Pretty much what we expect. If we come in, we hit it with a bunch of extra hits, it gets darker, and it gets a little bit slower. Okay? What can we do when we're looking at column families and seeing what the differences between those are? Well, inherently, two column families are probably created for different purposes. You store your user accounts in one, you store an address or a transaction record in another. The frequency that you're going to be hitting your user accounts probably much different than the frequency you're going to be hitting transactions, or you're going to be updating address information. So just usage patterns are going to be very different when you're looking at two different column families. So then it kind of comes in as like, all right, is this an expected difference, or is this something that is much more of a temporal difference? Because one column family is behaving differently than another from an operational standpoint. Compactions happen on a column family, okay? Read repairs happen on a column family. These are kind of things where it's like, you look at a particular section, you can have them fire off at the same time if you really want to slow everything down, but you're going to be distributing them, and so if you look at what's there, you're going to expect to see slight differences just based on timing. Other things that can kind of come up when inherent differences, just listing them, as we said, usage patterns. Usage pattern also leads or stems from your consistency level. If you're reading at quorum, If you have a replication factor 3 and you're reading at quorum, you're going to expect to see at least twice as many hits on a column family versus another column family. And that's if they were receiving the same amount of front-end requests, right? If you're doing, you expect to see twice as many versus a column family where you're reading at a consistency level 1, right? So just that usage changes the overall package. And again, there can be temporal issues with systems. Maybe a disk starts to have, hits a sector and has a bunch of different errors. You can start seeing that. If that's limited to a particular column family and that column family is allocated to a bunch of disks, that can be an indicator as well. So going back to the heat maps, what do these look like? Pretty straightforward. If we have a usage difference, a consistency level difference, and actual raw request rate difference, we're going to expect to see one column family be much hotter than another column family. In addition, column families that have, the same kind of distribution, or from an overall from an overall quantity amount, just changes in where that band appears. This can be due to the fact that one column family is a wide row, and it's reading in many more SS tables just to read in the number of columns, versus another column family, which is a short row. It may be returning one value. That's going to be one SS table, assuming you have good compaction, et cetera, et cetera. So kind of the baseline here is, you have to understand what's happening with regards to your data model and your application and what it's reading to be able to piece these two together when you're just comparing them. Temporal differences tend to stand out. Anytime you're looking within one thing that should be behaving all the same and you see a temporal difference, you're going to expect that there's some kind of operational load due to it. Again, this could be front-end request changes. This could be, compactions, garbage collections. Well, garbage collection should affect both, but compactions, read repairs, anything which was going to be column family specific. So that kind of covered, when it comes down to it, again, there isn't a whole lot of different patterns you're going to see. The key that you're going to be looking at is the relationships between those patterns. So that's pretty much the extent of what you have for column families. The same thing when you're looking at, one column family that exists on two different nodes. You're going to have your inherent, you're going to have your temporal, both system as well as Cassandra application, as well as overall front-end requests, right? So inherent differences, different CPU, different disks, even different networking capabilities depending on the amount of requests going into it. You also have application usage. Given the way the partitioner spreads the load, when you're seeing hotspots, you're also going to be seeing potential latency increases. Just from the standpoint of there's more, even though they're all hitting the same thing and it's probably hitting it in memory and it's serving the same data out, you're still going to see a latency impact. May not be as profound as when you're, doubling your load on something, but you're still going to see some shift there. Temporal items, again, hardware issues are the easy ones to talk about, and then overall system maintenance issues. Backups coming from the system, tend to stagger those. Cron jobs, any kind of thing that does a lot of I/O on your data disks. If you happen to be commingling logging and data on the same disk and you run a log compression job, that's going to have impact on your reads and writes. And then the last thing, as we said, garbage collection is going to impact on a node-by-node basis. It's going to go staggering around the ring, hopefully, but it's still going to hit certain nodes at times when it's not hitting others. Compaction, column family versus node, that comes up. And then gratuitous flushing or just out-of-memory issues when you're pushing up on your heap sizes. You're going to see that in certain nodes before you see it in other nodes. This will also trigger those temporal changes in your pattern, in your heat maps. So that's column families, both from the single node and comparing it between each other, and also comparing different nodes. When you look at the storage proxy, what you're concerned about here is more the interaction between the cluster than it is any given read or write operation on a node itself. So there's one storage proxy, or the coordinator, for any given node. So all of your requests that are here, all of the data that you see here, it's going to be commingled. All right, it's hard to pull out, oh, this column family is behaving this way for its coordinator. This column family is behaving another way. The numbers just aren't there. It's not exposed. So that's one of the big things that you're looking at from a node level, is knowing that that's the wide range. You're going to have to keep in mind that you're looking for more coarse items. So what is some of that? Again, resources, because we're looking at nodes. But then we also go into, again, the application usage, triggering hotspots, consistency level, replication factors. Each of those can impact it. The other thing, since we're looking at the node basis and we're talking about the interaction between the coordinator and the storage components, token aware. There's been plenty of publishes which say if you're token aware, you should be running faster, right? This is demonstrable with inside of your storage proxy, inside of your storage proxy, but it won't be demonstrable inside of your column families, since it's only going local, or it's going as local as it can with regards to its requests. Same temporal systems as you'd see in column family from the node level, and then same temporal application level differences, compaction, flushing, garbage collection, triggering on the token aware connection imbalances. You're going to see that a lot more in the storage proxy as well. So everything up till now has been latencies, because the title of the talk is performance. So latency tends to be the big thing when it comes to performance in the histograms. The other aspect of that is your data patterns. Okay, SSTables, column count, and row sizes. These are column family metrics. So you go to any given node and you'll look at these values for the portion of the ring that column family has on that node. Okay. In general, the more SSTables you read from, the slower you're going to be. So you're going to want to see, any kind of histogram or heat map that has SSTables on it shying towards the 1 or 2 values. And you're going up to the 7, 8, 10, 12, 14 values. What you're starting to see is a lot of SSTable spanning. And that just means it's making at least, if you have 14 SSTables hit, you're probably doing 14 reads, whether those go to the virtual, go to disk or they're cached in memory. You're still doing 14 reads out to the virtual file system, versus something that only has 2 reads. You're going to see a big difference with regards to your response time. So again, in latency, we have this golden rule that lower is better, okay? When you're talking about data sizes and patterns, it's completely dependent upon your usage. 14 SSTable reads might be necessary based on what your application is doing and how wide its row is. But you really have to know that before you can go making some judgments on it. When you're looking at these particular values with regards to your, histograms, heat maps, these are going to give you some indicators that you might want to change your data model. You might want to change your usage pattern. But again, you have to make that decision for yourself. Okay. So again, remember your data model. So if you do see something like this SSTable spanning cropping up, ask yourself, should I be seeing spanning? If I'm writing one value to one row and never changing it, you shouldn't really see spanning. It should never have to go to multiple SSTables to read from that. If it is, something else is going on. You either need to look at what your compaction settings are, size versus level, obviously. Some of these behave better with regards to wide rows. Some of this behaves better for the standpoint of single writes never changes, right? If you have a lot of TTLs, if you have a lot of columns which get deleted, you're going to have a lot of tombstones. You're going to have a lot of tombstones showing up in your columns, in your SSTables. You're going to want to have to keep an eye on that, because that, again, will affect the number of SSTables that it's spread across. Again, if you see a lot of SSTables, you're probably, I'm just going to say you're probably leaning towards something that might not be good. You're going to see these anti-patterns. There's been the Q anti-pattern, which again is a lot of short-lived writes and overwrites, or reads and or writes and deletes, you're arbitrarily appending to a row without ever having any particular cutoff. So if you're doing time series data and you're always going back and referencing a row rather than splitting up your time series data into chunks and then saying this chunk will become cold storage effectively. That lets the compaction actually do its job rather than stretching these SS tables out. Row size, column count, again, no clear indicators whether this is good, bad, or other. Obviously, the larger a row, the more columns it has, the more latent the response will be, most likely. It's just more data. It has more to read in or write out. The other thing to keep in mind with these two in particular, they're estimates. They actually only change when there's an SS table flush or an SS table update. And then additions happen faster than deletions because it has to go up, and compaction will kick in with regards to when it's pulled out. So it's not always going to add up to what is the actual amount of valid data in a row, but it's something to keep an eye on. And then the other thing, again, tombstones, they're going to hide in there. But they're going to add to that row size. And again, if you're expecting only 100 bytes of data and you're seeing 10,000, probably something's hiding in there. So you have to ask yourself, are these your expected values? And is there any outlier? Are there 10,000 rows that are sitting at 100 bytes and one row that's sitting at 10,000 bytes? Is that good, bad? Is that what really should be happening in your table or not? You'll have to decide. So reiterating, histograms good, heat maps are better, mainly due to that aliasing. You can do histogram or heat maps based on some of the charts that I was doing. You can run CF histograms multiple times and collect that data and piece it together yourself. Take your pick. Histograms and heat maps are good about showing the form of your data, but not really giving you this is good, this is good or bad. You still have to make that decision. There aren't too many different forms that you can see with regards to these. The same three common patterns are really going to crop up. Again, know the difference between storage proxy and column family histograms. Think about what might be an inherent issue to your application usage and what might be a temporal issue. And then data model, data model, data model. It all comes down to that when you're talking about performance. So that's it. I think I have...